Okay, let's unpack this. In the world of machine learning, building a great model is, well, it's only half the battle, isn't it?
It really is.
The other half, the absolutely crucial part, is training it effectively. And that's where optimization algorithms come in. They are the engines, the navigators that help our models learn.
Yeah, figuring out the best way to adjust millions, sometimes billions of parameters based on the data.
They're kind of the unsung heroes of deep learning.
Exactly. But training these complex models on massive data sets, especially when the data might be noisy or, sparse, that's where a lot of the older approaches kind of hit their limits.
Finding something fast, stable, that works across different types of problems, that's a huge challenge.
A really massive challenge.
And that challenge led us to do a deep dive into a paper that introduced an optimization method that, well, it completely changed the game for a lot of people.
We're talking about Adam.
Adam, yes.
That's right. Our source material for this deep dive is the paper Adam, a method for stochastic optimization, presented at ICLR way back in 2015 by Kingma and Ba.
And this paper didn't just propose a new algorithm, did it?
No, not at all. It analyzed its properties, backed it up with some really solid empirical results that definitely made waves at the time.
So our mission today is to take this paper and really pull out the core of what Adam is, how it manages its adaptive magic, why it became such a go-to method.
And what key insights it gives us about optimization in general.
Exactly. Consider this your essential shortcut to understanding one of the most influential algorithms in modern ML.
Okay, so let's dive into the problem space first. A lot of machine learning involves optimizing what we call stochastic objective functions.
Stochastic, right, meaning there's randomness involved.
Precisely. Usually because we're only using small subsets of the data mini-batches at each training step, not the whole data set.
Okay, and the classic approach there is stochastic gradient descent, SGD. Calculate the gradient on a mini-batch, take a step. Simple idea.
Simple, yeah, but it can be slow or kind of jumpy or even get stuck, especially if you have noisy gradients or if different parameters really need vastly different step sizes to learn well.
Which happens a lot in deep networks.
Oh, absolutely. And that's pretty much the void Adam stepped into. The paper presents it as a method for first-order gradient-based optimization.
First order just meaning it uses the gradient, the first derivative.
That's it, just the gradient to decide where to step. Keeps it computationally efficient compared to methods that try to use, like, curvature information.
But the real innovation, the big idea that set it apart.
It computes individual adaptive learning rates for every single parameter in the model.
Wow, okay. Not just one rate for the whole model or one per layer, but truly one for each weight, each bias.
Exactly. And its name, Adam, is actually a clue to how it does this. It stands for Adaptive Moment Estimation.
Adaptive moment estimation. Okay, so it adapts the steps based on estimates of moments of the gradients.
You got it. Lower order moments specifically.
All right, so how does it actually estimate these moments and then use them to figure out the step size for each parameter? Let's get into the mechanics.
Okay, so it keeps track of two key moving averages over time. First, there's MT. This is an exponential moving average of the gradients themselves.
So like the average direction the gradient has been pointing for that parameter?
Kind of, yeah. It's an estimate of the mean of the gradient, the first moment.
Got it. And the second one?
That's VAT. It's an exponential moving average of the squared gradients.
Squared gradients. Okay, so that's related to variance.
Exactly. It's estimating the uncentered variance of the gradient for each parameter. Basically, how much the magnitude of the gradient for that parameter tends to jump around. The second raw moment.
In these averages, they have hyperparameters controlling them.
Yep, beta 1 and beta 2. Beta 1 controls the decay rate for MT, the first moment average, and beta 2 does the same for VT, the second moment average.
Higher beta means it remembers more history, makes it smoother.
Right, smoother, but also slower to react to sudden changes in the gradients. Lower beta, it adapts faster but might be noisier.
Now, here's where the paper apparently pointed out a really critical challenge and came up with a neat solution. Initialization, right?
Absolutely. When you start training, these moving averages, MT and VT, are usually just initialized to 0.
Okay, seems simple enough.
But it means the early estimates are actually biased towards 0, especially if you choose those beta values to be close to 1, which you often want for stability and handling sparse gradients.
Ah, I see. If beta 2 is close to 1, VT starts tiny. And since the update rule divides by the square root of VT.
You could get ridiculously large, unstable steps right at the beginning of training. It could just explode.
Okay, that sounds bad. So what's the clever fix? This is where it gets really interesting, I heard.
It is pretty clever. The paper introduces a simple but really effective bias correction. It's applied to both moment estimates, giving you MAT and VOT.
Bias correction. How does that work conceptually?
The intuition is kind of like dividing by how much history you haven't seen yet. At the very first step, T1, you divide by a term that reflects you've only seen a tiny fraction of the history, based on beta.
Okay.
As time goes on, as it gets bigger, this correction factor gets closer and closer to 1, and the bias basically disappears.
So to adjust those early zero-biased estimates to be more realistic right from the start.
Exactly, making them more reliable when you most need it in those crucial initial steps. The actual formula involves dividing the raw estimate by 1 beta, where it is the time step.
Don't need to memorize the formula, but the impact sounds huge. It stabilizes things early on.
Hugely important, especially if you pick beta values close to 1, maybe for dealing with sparse gradients. This correction prevents those wild initial steps.
Okay, so we've got these stable, bias-corrected estimates. M hat for the mean, vet for the uncentered variance. How does Adam combine these to actually update the parameters? Theta.
The update rule itself is quite elegant. For each parameter, you take a step. The direction is given by the bias-corrected first moment. That's your average gradient direction.
Makes sense. Go in the average direction.
But then you scale that step. You divide half hat by the square root of the bias-corrected second moment, squart fat.
So the step size gets smaller if the variance hat is larger.
Precisely. That's the adaptive scaling kicking in. It uses the estimated variability to adjust the step size for that specific parameter.
And then there's an overall learning rate, alpha.
Yes, you multiply that whole thing by the global step size hyperparameter, alpha.
So hat says go this way, and squart fat says, but only take a step this big for this parameter based on how jumpy its gradients have been.
You nailed it. A parameter with consistently large gradients will build up a larger VAT, which shrinks its effective step size. A parameter with smaller or less consistent gradients gets relatively larger steps. It's adaptive step sizing, individually tuned.
That leads us perfectly into Adam's properties and advantages. The most obvious one is that per parameter adaptive step size we just discussed.
Right. And the paper points out something neat. The effective step magnitude, like how far you actually move in parameter space, is roughly bounded by that global alpha.
Okay.
They even talk about the ratio MESHAT score as being like a signal-to-noise ratio for the gradient direction.
Signal to noise.
Interesting. Yeah, if this ratio is small, meaning the gradient direction is less clear, maybe more noise relative to the signal, Adam naturally takes smaller, more cautious steps.
So it sort of automatically slows down or becomes more careful when things are uncertain, like a built-in annealing.
Exactly. Without needing a complex, manually tuned learning rate schedule quite as much, it adapts.
That's cool. And I remember reading about a surprising property related to rescaling gradients.
Oh yeah, that's quite elegant too. Adam's effective step size is actually invariant if you just scale the gradient itself.
How does that work?
Well, if you multiply the gradient g by some constant c, then m hat, the average gradient, gets scaled by c. But vat, the average squared gradient, gets scaled by c squared.
Oh.
So when you calculate the update hem hat squared, you get cm hat c2 vat, which simplifies to cm hat c squared or vat. C is just cancel out.
The step magnitude stays the same. That adds some robustness, I guess.
Definitely. It means Adam isn't sensitive to the overall scale of the gradients, just their relative consistency and direction.
What other benefits did the paper highlight? Seems like there were quite a few.
They listed several, yeah. It's memory efficient, just needs to store MT, VT, and the parameters themselves.
Compared to methods storing more complex info, like Hessian's.
Right. It's computationally cheap per iteration. Straightforward to implement. Works well for problems with tons of parameters or huge data sets, and it's good for non-stationary objectives.
Non-stationary. What does that mean in practice?
Think about using techniques like dropout during training. Dropout randomly switches off neurons at each step.
Right, so the network architecture, and thus the function you're optimizing, changes slightly all the time.
Exactly. That's a non-stationary objective. Adam handles that kind of dynamic environment well, where some other methods might struggle.
Okay. And it also inherits strengths for noisy or sparse gradients.
Yes, it builds on ideas from methods like Adagrad, making it quite effective when gradients are sparse, like with word embeddings or one-hot encoded features.
And the hyperparameters, alpha, beta 1, beta 2, epsilon, Are they a nightmare to tune?
Well, the paper suggested they're often less sensitive than hyperparameters and other methods. They even provided default settings that work surprisingly well across a range of problems they tested.
I think I remember those defaults. Alpha 0.001.
Yep, alpha 0.001, beta 1 equals 0.9, beta 2 0.999, and a small epsilon equals 10 to 8 just to prevent division by zero. Those became really common starting points for a long time.
Makes sense. Okay, the paper also situated Adam relative to earlier optimization methods, didn't it? It wasn't created in a total vacuum.
Absolutely not. It was clearly inspired by and combines ideas from existing methods, particularly RMS-prop and Adagrad.
Okay, let's start with RMS-prop. What's the connection there?
Well, RMS-prop also uses a running average of squared gradients to scale the learning rate, similar to Adam's VT.
So what's the main difference?
A key difference often cited is how momentum is potentially incorporated. RMS-prop with momentum might apply momentum after rescaling the gradient by that squared average. Adam uses the moment estimates, m-hat and vat, directly in its single update rule.
And the bias correction. That was a big differentiator, wasn't it?
Crucially, yes. Standard RMS-prop lacks that bias correction term.
And the paper argued this matters.
A lot. They showed that without bias correction, especially if you set beta 2 close to 1 for smoother estimates, the early VT values stay biased towards 0 for too long,
Leading to those unstable large steps we talked about earlier.
Exactly. Potentially divergent updates right at the start. The bias correction in Adam is a major reason it tends to be more stable early in training compared to RMS-prop in many scenarios.
Okay, that makes sense. What about Adagrad? Adagrad was known for handling sparse gradients really well.
Right, and Adam shares that strength. The paper draws a conceptual link. You can sort of see Adagrad as a specific instance of Adam if you set beta 1, 0, no first moment averaging, make beta 2 effectively approach 1 infinitely slowly, like 1 epsilon, and use a decaying alpha.
But there's a catch.
Again, the bias correction. The paper points out this connection only really holds because Adam has the bias correction. If you tried to make an Adam variant like Adagrad without the correction and set beta 2 near 1,
You get infinite bias and infinite update.
precisely, the update would blow up. So the bias correction isn't just a minor tweak. It's fundamental to Adam's stability and its ability to generalize ideas from Adagrad while using beta 2 values close to 1.
Really underscores the importance of that detail. Okay, so the theory and connections seem clear. But the proof is in the pudding, right? How did Adam actually perform in the experiments reported in the paper?
The empirical evaluation was pretty thorough, yeah. They tested Adam on various machine learning models and data sets. Yeah.
And the verdict?
Consistently, it worked well. It compared favorably against the competitors they tuned, like SGD with Nesterov momentum, Adagrad itself, and even a more complex method, a quasi-Newton optimizer called SFO.
What about on simpler, maybe convex problems,
Yeah.
like logistic regression on MNIST?
On MNIST, which is a non-sparse convex problem, Adam was basically as fast or sometimes faster than tuned SGD with Nesterov momentum.
Okay, competitive there.
Well,
What about sparse data?
they used the IMDb dataset with bag of words features very sparse. There, Adam converged as fast as Adagrad, which is specifically designed for sparsity, and it significantly outperformed SGD with momentum.
So that supported its ability to handle sparsity well, just like Adagrad.
Exactly. It showed it wasn't just good on dense problems.
What about harder non-convex problems, like standard multilayer neural networks?
Yeah, on MNIST with MLPs, Adam often showed stronger performance empirically. It made faster progress than that SFO method, the quasi-Newton one.
Which tries to use curvature information, right?
Right, but SFO is much more computationally expensive per iteration and needs way more memory. Adam was faster overall.
And Adam handled things SFO couldn't.
Crucially, yes. Adam worked perfectly fine with stochastic regularization, like dropout, that non-stationary objective thing again. SFO, being designed for deterministic functions, basically failed when dropout was introduced.
Makes sense. Adam's adaptive nature just fits better with that kind of randomness. What about convolutional neural nets, CNNs? They have their own quirks, like shared weights and different layer dynamics.
Good question. On CNNs, like training on CFAR10, the results were interesting. Both Adam and Adagrad started off fast, getting low error quickly.
But over the longer run.
Over more epochs, Adam and SGD eventually converged faster and often to slightly better solutions than Adagrad.
Any insights why?
They noted an observation. Sometimes in CNNs, the second moment estimate, VACAT, seemed to become less informative about the actual geometry compared to fully connected nets. The variance across mini batches might shrink. In those cases, maybe reducing the noise via the first moment estimate became more important than the second moment scaling. But a big practical win for Adam here was its automatic adaptation of learning rates, layer-wise.
Ah, so you didn't need to manually fiddle with different learning rates for convolutional versus fully connected layers as much as you might with SGD.
Exactly. Adam handled that adaptation automatically, which is a big convenience.
And they did run a specific experiment just to really nail down the importance of that bias correction.
Right. They did, using a variational autoencoder, or VAE, a more complex generative model.
And what did it show?
It showed very clearly that if you set beta 2 close to 1, which is often good for robustness and handling sparsity training, became unstable or even diverged without the bias correction, especially early on.
But with the bias correction.
Adam performed well and remained stable, regardless of whether beta 2 was moderate or close to 1. It was a direct comparison showing the practical value of that correction term, making Adam more robust than a version without it, which would be more like RMS prop with momentum.
A very clear demonstration. Okay, before we wrap up, the paper mentioned a couple of extensions or related ideas briefly.
Just briefly, yeah. One was AdamX.
AdamX, what's the idea there?
It's a variant of Adam that uses a different norm for the second moment estimate. Instead of the L2 norm, squared gradients, it uses the L infinity norm, which basically means tracking the maximum absolute gradient seen so far with exponential decay.
How does that change the update?
It leads to a surprisingly simple update rule for its equivalent of VAT. Let's call it OutDat. It's just APID max, beta 2 UT1 GAT. Take the max of the decayed previous max and the current absolute gradient.
Interesting. And does it need bias correction?
For that second moment part, AdamX actually doesn't require the bias correction, so
Yeah.
slightly simpler in that regard.
And the other idea mentioned was temporal averaging.
Right, that's a general technique sometimes used in optimization, not specific to Adam, where you average the model's parameters over the later stages of training. It can sometimes improve generalization.
And the paper just noted you could add this to Adam easily.
Yeah, they suggested it could be easily bolted onto Adam. You could maintain either a simple running average of the parameters, theta, or an exponential moving average. And again, if using an EMA for the parameters, they noted you might want to apply bias correction to that average too.
Okay, interesting add-ons. So wrapping up this deep dive then, what's the core takeaway? What's the ultimate value Adam brought?
I think it provided a remarkably efficient, robust, and just broadly applicable optimization method. It cleverly combined these running averages of gradient moments, added that crucial bias correction.
Resulting in per-parameter adaptive learning rates.
Exactly. And that combination just worked really well across a huge range of machine learning problems, from logistic regression up to complex neural networks. It significantly simplified the optimization process for many people.
Yeah, it really did become a default choice, or at least a very strong baseline for a long time, didn't it? Built on the shoulders of giants like RMS Prop and Adagrad, but fixed some key issues like that initial instability.
A genuinely significant contribution to the field, no doubt.
It makes you think, doesn't it? Consider how seemingly small mathematical details, like figuring out how to correct for bias when you start an average from zero, or carefully adapting step sizes based on past gradient behavior, how these things can have such a profound impact on our ability to actually train these incredibly complex models effectively.
Yeah. The details matter.
What other small details, maybe overlooked aspects in how we build or train models today, might hold the key to unlocking even greater capabilities in the future? Something to ponder.